So today I'm going to review you with trigonometry. So first, let's have the different ratios for a right triangle. So the keyword here is SOHCAHTOA. So if you can remember, this means that sine of an angle theta is equal to opposite over the hypotenuse. And this sine theta here is also equal to B over C, opposite side B over C, and because this angle here is the complementary angle of theta or co-theta or 90 degrees minus theta. So sine theta is also equal to cosine of 90 degrees minus theta, and the reciprocal of cosecant theta. So sine theta is also 1 over cosecant of theta. Then cosine theta, which is equal to adjacent side A over C, it is also equal to sine of 90 degrees minus theta, and it is equal to 1 over secant of theta. Then tangent theta, which is opposite over adjacent, so it is B over A, which is also equal to the cotangent of 90 degrees minus theta, and for the cotangent of this angle, it is B over A, and it is also equal to 1 over cotangent of theta. Then we have cotangent theta, which is adjacent side over opposite, so A over B, which is equal to tangent of 90 degrees minus theta, which is 1 over tangent of theta. Then secant of theta, which is equal to hypotenuse C over adjacent A, so it is equal to cosecant of 90 degrees minus theta, which is also equal to 1 over cosine of theta. Then finally, cosecant of theta is equal to hypotenuse over opposite, and therefore it is also secant of 90 degrees minus theta, or 1 over secant of theta. Then we have the Pythagoras theorem, which is the sum of the squares of the perpendicular legs is equal to the square of the hypotenuse. So in this case, a squared plus b squared equals c squared. Dividing everything by c squared, and you'll have a over c quantity squared plus b over c quantity squared equals c over c quantity squared. Since a over c is cosine theta, so this is cosine squared theta plus sine squared theta, and of course the right side is equal to 1. So that's the fundamental identities, one of the fundamental identities. So we have cosine squared theta plus sine squared theta equals 1. If we divide everything by sine squared theta, and noting that cosine over sine is cotangent, and because this is squared, so dividing everything by cosine squared theta, so we have 1 sine over cosine is tangent, so we divide first by sine squared theta, so cosine over sine is cotangent, so we have cotangent squared theta, sine square over sine square is 1, equals 1 over sine square is cosecant squared theta. So another identity is cotangent squared theta plus 1 equals cosecant square of theta. If instead we divide everything by cosine squared theta, so we have 1 sine over cosine is tangent, so 1 plus tangent squared theta, and 1 over cosine squared theta is secant squared theta. So 1 plus tangent squared theta equals secant squared theta. Then we have the sum formulas. So sine of alpha plus beta equals sin cos plus sin, or sine alpha cosine beta plus cosine alpha sine beta. Cosine of alpha plus beta is cos cos minus sin sin. Cosine alpha cosine beta minus sine alpha sine beta. Then tangent of alpha plus beta is tangent of alpha plus tangent beta all over 1 minus tangent alpha tangent beta. So that's the sum formulas. Next, we have the standard position of an angle. The angle is said to be in its standard form when the angle is measured counterclockwise because counterclockwise direction is positive. So if these are the different positions of an angle theta. So in the first quadrant, theta is positive because that's counterclockwise, measured counterclockwise. This is the terminal side. The hypotenuse is the terminal side of the angle. Then if the terminal side lies in the second quadrant, then this angle here is the standard position. That's the positive angle. So if the angle remains theta, if this is theta here, this acute angle here is still theta, then the angle is positive quantity 180 degrees minus theta. Now, if the terminal side lies in the third or in the fourth and you measure it clockwise, then the angle is negative. So, like this terminal side here, which lies in the fourth quadrant, and we measure it clockwise, so it is negative of theta. So the angle theta, the acute angle theta, is called reference angle. So again, theta is positive in counterclockwise direction. So therefore, in clockwise direction, it is negative. And also, theta is negative in the clockwise direction. Then from the figure, so the acute angle theta is called the reference angle. From the figure, sine of positive theta is equal to, or sine of negative theta is equal to opposite, which is negative b over r. R, by the way, is square root of a squared plus b squared, and it is always positive. So sine of negative theta is opposite negative b over r, but the ratio positive b over r is equal to sine theta. Therefore, sine of negative theta is negative sine theta. Likewise, cosine of negative theta is positive a over r. So cosine of negative theta remains cosine of theta. Then tangent of negative theta is equal to negative b over a, opposite over adjacent, but opposite is negative b. Therefore, it is equal to the negative tangent of theta because b over a is tangent of theta. So there is because b is negative, so it is negative tangent theta. Cotangent of negative theta is a over negative b, or let's begin with cosecant of negative theta first. It is r over negative b, and the ratio r over positive b is cosecant theta, so there is a negative sign here, so therefore it is negative cosecant theta. And next, reciprocal of cosine is secant. So secant of negative theta is r over positive a. Then r over positive a is same. It is equal to secant of theta. Then we have cotangent of negative theta, which is a over negative b. And therefore, it is equal to the negative of cotangent theta. So we notice that only cosine and secant remains the same even if the angles are negative or in clockwise direction. So we call these functions, secant and cosine, as even functions because they do not change when the function value is replaced by a negative value, while all the rest, sine, cosecant, tangent, and cotangent, are called odd functions. If you can recall your analytic geometry or even in trigonometry. Next is the double angle formulas. So here, if we replace alpha and beta by theta, so the angle is doubled. So theta plus theta. So this is sine 2 theta. Then we have sine theta, cosine theta, plus cosine theta, sine theta. These are like terms. Therefore, sine 2 theta is equal to 2 sine theta, cosine of theta. Then here, if we replace alpha and beta by theta and theta, then we have cosine of 2 theta equals cosine theta, or cosine square theta minus sine theta, so minus sine square theta. So cosine 2 theta equals cosine square theta minus sine square theta. If we replace cosine square theta by its identity here, which is 1 minus sine square theta, then we have another formula for cosine 2 theta, which is equal to 1 minus 2 sine square of theta. If instead we replace sine square theta by its identity, which is quantity 1 minus cosine square theta, so another formula for cosine 2 theta would be equal to 2 cosine square theta minus 1. So that's the double angle formulas. Next, we have the up. Then, by the way, here, tangent of theta plus theta is tangent to theta. Then we have tangent theta plus tangent theta. So we have 2 tangent theta all over 1 minus tangent theta, tangent theta. So we have 1 minus tangent square theta. And next, we have the half angle formulas. So these half angle formulas will be derived from this double angle formula. So we simply replace theta here by half. So this becomes theta over 2. And this is 2 times theta over 2. So this becomes cosine of theta. So if we derive for sine theta over 2, so we have 2 sine square of theta over 2 equals 1 minus cosine 2 theta. Therefore, sine of theta is equal to plus minus square root of 1 minus cosine theta over 2. So that's the formula for half angle formula for sine theta over 2. Likewise, for this equation here, if we replace theta by theta over 2, and this becomes cosine of theta, then plus 1, 1 plus cosine theta is equal to 2 cosine square of theta over 2. So solving for cosine theta over 2, it is equal to plus minus square root of 1 plus cosine theta over 2. Then, because tangent of theta over 2 is sine theta over 2 divided by cosine theta over 2, so this square root of 2 in the denominator here will cancel out. So tangent of theta over 2 is equal to plus minus square root of 1 minus cosine theta over 1 plus cosine theta. That's it. Then for the difference formulas, so all you have to do is replace in this sum formulas here, we replace beta by negative beta. So that becomes sine of alpha plus negative beta, or sine of quantity alpha minus beta. Remember that the cosine of negative beta remains cosine of positive beta, while the sine of negative beta is the negative sine of beta from these negative relations here. So therefore, sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. Similarly, for cosine, we replace beta by negative beta, and cosine of negative beta remains cosine of positive beta. Then this sine of beta here becomes sine of negative beta. So negative, which is negative sine beta times negative, so positive. So cosine of alpha plus beta becomes cosine alpha cosine beta plus sine alpha sine beta. And finally, for tangent, replacing beta by negative beta, so we have tangent of alpha minus beta is equal to tangent of alpha plus tangent of negative beta. But tangent of negative beta is equal to negative tangent beta. So this becomes minus, so tangent alpha minus tangent beta all over. Again, tangent of negative beta is negative tangent beta. So negative times negative positive. So tangent of alpha minus beta is tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. So that's the technique. You don't need to actually memorize everything. There's the technique here on how to memorize trigonometric function values, identities, and sum formulas, difference formulas, double angle formulas, half angle formulas, and so on. So that's it. So next, let's derive, or I discussed the law of sines, the derivations also, and some other matters. So let's consider a triangle ABC. The angles are angle A, this is angle B, and this is angle C. And we have here a circle circumscribing about the triangle, and we call this circumcircle. The center of this circumcircle is this point O here, which is called circumcenter. And from plane geometry or in trigonometry, the circumcenter is simply the center of the circumscribing circle about a triangle, or the other definition, it is the point of intersection of the perpendicular bisectors of the side. So if this is side A, you locate the midpoint. So from B, half of A is A over 2. Then you draw a line perpendicular to side A, then it will cross point O. Same is true with this triangle here, because these triangles are isosceles triangles. So obviously, the perpendicular bisector of the bases or the sides will pass through the circumcenter or point O. So that's the other definition. So from this figure, uh, we have sine of, because if this is angle A and this is an isosceles triangle, the angle A subtends arc BC, so therefore the central angle which subtends the same arc BC is equal to double of angle A. So this angle here about O is equal to 2 times angle A. So that is 2 times angle A. Likewise, this angle here is equal to 2 times angle B, because B subtends this arc. So the central angle will be double that uh, angle measurement. So this is 2 times angle B. So of course, the remaining angle is equal to 2 times angle C. So to prove that these are all correct, you add 2 times angle A plus 2 times angle B plus 2 times angle C. So that's a whole circle or full angle. So it is equated to 360 degrees. So divide everything by 2. So angle A plus angle B plus angle C is equal to 180, which is true. The sum of the interior angles of a triangle is equal to 180 degrees. Since triangle BCO is an isosceles triangle, so if we draw a line from point O perpendicular to A, so that's why it's called point O is circumcenter, the point of intersection of the perpendicular bisectors of the sides of the triangle. So we have a right triangle, then the measure is half of 2 angle A, so angle A, and the opposite would be half of A. So A over 2 divided by the hypotenuse, which is the radius of the circumscribing circle. So sine angle A is equal to opposite A over 2. So again, we have to drop a line perpendicular to BC. Remember, this is an isosceles triangle, so therefore that line from point O perpendicular to BC will form a right triangle which is 90 degrees at the point of intersection of the midpoint of BC. So that sine of angle A, half of 2 angle A, is equal to opposite A over 2 divided by R. Similarly, sine of angle B is opposite B over 2 divided by 2 divided by R. So B over 2 divided by R is B over 2R. And finally, sine of angle C, from this isosceles triangle here, you draw a line from point O perpendicular to side C. So it passes to the midpoint and the angle is bisected. So sine angle C is equal to opposite C over 2 divided by hypotenuse R, or simply C over 2R. Equating 2R, so from this equation here, 2R is equal to A over sine angle A. from this equation 2r equals b over sine angle b, and from this last equation 2r equals c over sine angle c. So that is the law of sines. 2r equals a over sine angle a equals b over sine angle b equals c over sine angle c. So that's the law of sines. Next, from this right triangle, we conclude that in any right triangle, the hypotenuse is equal to the diameter of the circumscribing circle about the triangle. So it is equal to 2r because when angle C, for instance here, it's 90 degrees, sine of 90 degrees is 1. So we conclude that because C over sine 90 is just C, so C equals 2r. So that's the proof that that in that the hypotenuse of a right triangle is simply the diameter of the circumscribing circle or the diameter of the circumcircle. In any triangle also, the longest side, for instance, the hypotenuse is always less than the shorter side. So in this case, C is less than A plus B. So in this triangle, if it is B, which is the longest side, then B is less than A plus C. So that's the fact about any triangle. Then we have the law of cosines. So before deriving the law of cosines, let's have a triangle again. Then from point B, we drop a line perpendicular to the base. So let's make the base horizontal for simplicity. Then we form two right triangles here. So the left side and we have the right side, right triangle. Then the angles, interior angles are angles A, B, and angle C. By the way, the interior angles of a triangle are also called inscribed angles or peripheral angles. So by calling this as x, because this whole length is b, so this side here is b minus x. Then we have sine of angle A is equal to opposite HB over C. Sine angle C is equal to opposite HB over hypotenuse. The hypotenuse of the right triangle, this right portion of this right triangle is equal to HB over A. So equating HB, so we have C sine angle A equals A sine angle C. So that's why we form this law of sines here, another derivation. So we have A divided by sine angle A is equal to C over sine angle C. So we simply extend it to B over sine angle B, which is equal to the diameter of the circumscribing circle. So this is the other way of deriving the law of sines. Then the area of the triangle, which is 1/2 base times height. So in this case, 1/2 B times h sub B. And we know that HB is C sine angle A. So therefore, the area of triangle is simply 1/2 BC sine angle A. But do not memorize it that way. You memorize the area of the triangle in this way. It's very simple to remember. It's simply 1/2 the product of adjacent sides times sine of the angle included between those sides. So for instance, area of triangle is 1/2 B and C, because B and C are adjacent, then sine of the angle between them, which is sine angle A. So it is 1/2 A times C adjacent, then the angle is B, so 1/2 AC times sine angle B. It is also 1/2 AB sine angle C. So as simple as that. So that's it. So by Pythagoras theorem again, we have HB square equals hypotenuse square minus the other leg, perpendicular leg, x squared. So HB square equals C square minus x square. HB square is also from this right triangle, A square, hypotenuse square minus B minus x quantity square. So equating these two, simplify this right side here, we have C square minus x square equals A square. The expansion of this binomial is quantity b square minus 2bx plus x square. So when you distribute the negative sign, so that becomes a squared minus b squared plus 2bx, then minus x squared. So c squared minus x squared equals a squared minus b squared plus 2bx, then minus x squared. So we can cancel out x squared because they have the same signs. Then transposing negative b squared to the left and 2bx to the left. So we say that a square here is equal to b squared plus c squared minus 2bx. And from the figure in this right triangle, because x is equal to hypotenuse times cosine of angle A, so replacing x by c over cosine angle A, so that now forms one cosine law formula. So a squared equals b squared plus c squared minus 2bc cosine of angle A. So it's not that you have to memorize cosine law in that manner symbolically, but there's a technique also. This formula says that any side square is equal to the sum of the squares of the other two sides, the sum of the squares of the other sides, then minus twice the product of these other sides, then times the cosine of the angle opposite to this side A here. So therefore, we just familiar one formula. So therefore, a squared equals b squared plus c squared minus 2bc cosine angle A. Then b squared equals a squared plus c squared minus 2ac cosine of angle B. Then c squared equals a squared plus b squared minus 2ab cosine of angle C. So that's the law of cosines. Then, by the way, remember that the law of cosines is absolute, meaning to say there's no problem with the law of cosines. It will give you the correct elements of the triangle. However, for the law of sines, there is an ambiguous case, if you can remember, especially when you solve for the angle. So if the angle is obtuse more than 90 degrees, so be careful in using the law of sines because I will demonstrate it later about the angle and its supplement relationship. So anyway, the law of sines is you have to be very careful, especially if there is an obtuse angle. So for instance, the angle is obtuse and you keep on solving the triangle using your calculator. So if you are accustomed to your calculator, so be careful because remember, if the angle is obtuse, for instance, it is 130 degrees, your calculator will give you an answer which is equal to 50 degrees. So if you have your calculator there, not the high-tech one, so you have to uh, remember that you have to train yourself not to use the high-tech one because that is not allowed anymore in the board exam. So sine of 30 is equal to sine of 150 degrees. Sine 30 is 1/2. Sine of 150 degrees is 1/2. So if the angle is obtuse and you use your calculator, if you shift solve or if you press inverse sine of 1/2, it will give you 30 degrees, not 150 degrees. So that's why you have to be very careful when you use law of sines and you notice that there is an obtuse angle. So it is very crucial when the angle is obtuse, more than 90 degrees angle. So that's only the restriction, that's only the problem with the law of sines. But if you don't want to have a problem like that, a situation like that, then apply law of cosines as much as possible. Then we have supplementary relations. This is what I mean for the ambiguous case. Sine of 180 degrees minus theta, if you use the difference formulas by expansion. So we have sine 180 degrees cosine of theta minus cosine 180 degrees sine of theta. Sine 180 degrees is 0, so this first term here would be 0. Cosine of 180 degrees is negative 1. So negative of negative 1 is positive 1. And 1 times sine theta is sine theta. So that's why sine 180 degrees minus theta is simply the sine of the angle theta. This is what I told you before a while ago. That sine 150 degrees is equal to sine 30 degrees. So sine of 40 degrees is equal to sine of 140 degrees because 40 and 140 are supplementary angles. The sum is 180 degrees. So sine 150 is 1 half, sine 30 is also 1 half. This is what I mentioned a while ago, that be careful to use law of sines when the angle, if you know that the angle is obtuse. But if you know the angle is obtuse and you use law of sines, if you are aware of that, then you have to add or you have to subtract the answer from 180 degrees. So for instance, you expect that the angle is obtuse and it will give you an angle of 20 degrees. So you do not make 20 degrees as your final answer. It should be 180 minus 20, so 160 degrees. Then this is it. So sine theta is equal to sine of 180 degrees minus theta. Properties of a parallelogram. So I'll discuss this first because this is important in the study of forces later on. So we have parallelogram, no? Remember? One axiom of mechanics. So if this is the parallelogram with dimensions A and B, so opposite angles are equal definitely. So this angle here is equal to that angle there. So because this side is this line is the extension of this side, and this side here is parallel to A, that's equal to A also. So therefore this is also theta. And because this angle theta and this interior angle of the parallelogram is a straight line or form a straight line, therefore this is 180 degrees minus theta. So that means that opposite angles are equal, adjacent angles are supplementary. In other words, theta. So this should be 180 degrees minus theta, or the sum of these adjacent interior angles is equal to 180 degrees. So the fact that opposite angles are equal, so this is also 180 degrees minus theta. And long diagonal should be, this is the longer diagonal. The longer diagonal should be greater than square root of a square plus b square. And, oh sorry, yes, square root of a square plus b square. And the short diagonal is less than, this one is less than square root of a square plus b square. So that's it about uh, parallelogram, properties of parallelogram. Then let's have some more important principles and concepts. This time, let's proceed to statics. So if you encounter this situation here, we have an angle of inclination theta, and this is the inclined plane. Then if a line is perpendicular to this inclined plane, so this point here, then we know that this angle here is the complement of theta, or 90 degrees minus theta. So this line is perpendicular to this inclined plane here. So this is the vertical line, and the measure of this angle is 90 degrees minus theta, right? So therefore, because this angle plus this angle is equal to 90 degrees, this is equal also to this. So therefore, this angle here must also be theta. So this is theta. and that angle there is also equal to theta. In short, or to generalize, the angle formed between a vertical line and the line perpendicular to an inclined line is simply equal to the angle of inclination of the inclined plane. So again, the angle between the vertical line and the line perpendicular to the inclined plane is equal to the angle of inclination of that inclined plane. So I hope you get that and you can remember that always, especially in solving systems of forces later or as you move on. So I just emphasize this moment of a force because you might not encounter this before. So moment of a force is a vector quantity which is the product of a force and the perpendicular distance between the line of action of the force and the point on the body about which the body tends to rotate. So if this is the wrench, for example, then we have imagine this is your hand, you have to uh, tighten the bolt. So you must exert a force to tighten the bolt, especially if it is already tight and you want to make it more tight. Then this is the moment arm, the perpendicular distance, that's the force. So this is called the moment arm, the perpendicular distance d. Then when you apply this force, this moment arm tends to rotate in counterclockwise direction. So therefore, the sense of moment is counterclockwise. And the value or magnitude of that moment of a force is simply the product of the force you exert and this perpendicular distance or called moment arm. By the way, this point here about which rotation tends to or about which rotation is possible is called the moment center. So that's all. Moment is simply F times D because it is a vector because of the force part. This force here, force is a vector, therefore it should be coupled with a direction. So the direction is the sense is counterclockwise. Why counterclockwise? You just imagine the rotation of the moment arm when you exert the force. So because this moment arm or lever arm will rotate counterclockwise in the same sense as the force, then the rotation is counterclockwise. So D is called moment arm, O is called the moment center. Then, in general, if we have here the plane of the force, and we have here a point O, then that point actually is not a point, but rather an axis about which rotation occurs, or that point O in 2D appears as a point, but actually it is an axis perpendicular to the plane of the force. So to give you the picture, this is the moment arm D, and this is the axis about which F or this moment arm rotates. So axis about which D rotates and in that direction. So this would be the effect. That's the couple. The magnitude of that couple is equal to F times D, and the rotation is in that sense. Another representation of the couple is you position your right thumb towards the axis, which is outward. Then the curling, your forefingers will curl in the same sense as the rotation of the moment arm. And in other situations, this couple, which is equal to FD, is represented by double arrowheads, like that. So the direction of the double arrowheads is your right thumb, and the curling of your forefingers about that axis would be the direction or the sense of that moment. So to give you the idea, this is your right thumb, for example, and you look at your four fingers, the rotation or the curling of your four fingers will be in the same sense as the moment of this force here. So that's it for this